The purpose of this lab was to observe the motion of some object that is moving at the same speed without changing direction. In order to achieve this objective, I first captured a video of a ball rolling across a level plane and then uploaded said video to Tracker, a video analyst and modeling tool that allowed me to clearly analyze my observational data. Furthermore, I also used VPython to create a model that described my observations based on Newton's second law. The model produced in VPython was then used to adequately show the expected path of the ball in regards to a position versus time graph, along with the observed path according to data obtained through Tracker. As you can see from this position versus time graph, the experimental data and the model data line up nearly perfectly, both having a constant slope, suggesting that the ball indeed was rolled at a constant velocity, and also that the experiment accurately executed Newton's second law. This video shows the ball in motion. The blue calibration stick serves as a marker of the measurement of the ball's diameter in meters. In this case, the diameter is 0.1289 meters. Tracker then uses this measurement as a gauge for the ball's position at each frame throughout the video. In addition to the calibration stick, there is also an XY axis with the origin at the center of the ball. This axis serves to show the ball's position and also shows how the ball is moving in a straight line as the ball's path of motion travels directly upon the x-axis. As shown by the position versus time graph in the upper right-hand corner, the ball is moving at a constant velocity in the positive direction. We can infer this from the positive slope. If the axes had been flipped to show the ball moving along the negative x-axis, the ball would be moving in the negative x direction. However, the slope would still be the same, and it could still be determined that the velocity of the ball was constant in the positive direction. In order for VPython to run, there are a few changes that need to be made to the code, and we can find this information in Tracker. These are the initial conditions for both the position and velocity vectors. The position is found from the chart in Tracker that gives the position of the ball at time equals 0 seconds, and the velocity is found by following Newton's second law of motion. Newton's second law states that when an object is moving at a constant velocity, the sum of the forces, or F net, equals 0, which means we only need to solve for one velocity. We can then use the initial and final positions from the Tracker chart to calculate the constant velocity. It's then not possible to say how many pushes and pulls are added together to give the zero net force because the velocity is constant. Delta t is also equal to 0.033 seconds, as that is the increments in which the ball's position was taken. Our time boundary is then set to 0.825 seconds, as that is the length of the tracked movement. Lastly, Newton's second law is put into terms that Python can interpret. When the code is run, it produces the ideal model of the ball's movement. This graph compares the predicted velocity found with VPython, shown in red, and the observed velocity found with Tracker and Newton's second law of motion, shown in blue. As shown, the predicted velocity and the observed velocity nearly line up perfectly. This means that our experiment performed in the way that Newton's second law of motion predicted it would. The little difference that does exist is most likely due to inaccuracies in the placement of the mass points on Tracker. This discrepancy also could be due to the ball not rolling in a perfectly straight line. In conclusion, based on our observed and predicted velocities clearly shown in this graph, Newton's second law can be used to accurately predict the velocity of an object traveling at a constant speed and in one direction.